All right, so as I'm getting this computer set up, I believe everyone should have gotten an email about like where the links are to everything. This page shouldn't seem too foreign. If you haven't already, um, there's this green button on the side here. You can either choose to download the zip, or if you know your way around Git, you can clone it down. And the reason for that is that's how it's probably the easiest way to get all the data sets that we'll be using for the course today. Having said that, if you're like me and you just decided to, if you needed help installing Python, there is, you can Google Anaconda Python, and the easiest way I found was to download the Anaconda distribution for Python, but if you already have Python installed from other means, the only libraries I think you need would be Pandas, scikit-learn, that's only for the very end for modeling. Seaborn, we're really using that plotting library for datasets, and I forgot to mention Jupyter would be nice to have because that's what I will be using to teach you guys. Is through Jupyter Lab. So, but if you already have a system of, if you're using idle, because that's how I was taught, you can do that as well and just copy paste stuff over into a console. And is this done installing? So once you have this folder, I would say create a folder called notebooks or something to store your notebooks in. I'll be doing the course in a series of IPython or Jupyter notebooks. And this way, it sort of nudges you in the direction of don't put all of your files in one folder, sort of separate things out if you can. If you guys stick around for the sprints, there is a sort of like pain point that I have with working with notebooks in that it always treats the working directory like where the notebook is. So like there's some there's some things I like about notebooks. There's some things I don't like about notebooks, and I plan on writing a small module just to help relieve that pain point. Especially if you're working on Python, like on a local machine or on like a server, and you don't have anything weird going on like remote kernels and all of that stuff. So yeah, so create a notebooks folder. This is where I will be dumping the notebooks we'll have for the class, and then during each break or so, I can't push the notebooks because Git's not installed on this machine, but right after the class, I'll put up all the notebooks that we have from the class like up. If you really need to, as like an absolute fallback in terms of like something totally got missed, I would suggest like you not look at this stuff, just because it's way better to, at least in my experience, it's way better to sort of type out the commands and sort of see the common mistakes that you're making just by spelling things wrong. But there is a .notes folder on GitHub, so you can use that as a reference. But again, like I wouldn't just sit there and just think that you understand just by looking at the code. Like it really does help typing it out. And this is almost done installing. So I'll do a brief introduction to myself. My name is Daniel. I am your instructor for this morning. The materials that we'll be working on is based off of a book that I published, I think last year. It's called Pandas for Everyone. If you guys follow Twitter, like the box of books that I ordered for the conference came in yesterday. So like if you follow, there's like a board of open rooms or something. So sometime during the conference, I'll reserve a room and we'll just have it as a giveaway room. So just be on the lookout for that. Other things about myself, more recently I got my actual certification card to be a cave diver, so I am one of those crazy people that don life support equipment and go into dark holes under the water. So if you guys are scuba divers, be happy to talk. If you guys do dry caving, I'll be happy to talk. All right, so this looks like things are coming along. All right. For those of you who are, I'm going to assume that you are very, very new to at least the pandas / data science ecosystem stack. And so, how do we run this, or how do a lot of data scientists run this? If you installed Anaconda, there will be this thing called the Anaconda Navigator, and this should work for Windows and Mac. I think it exists for Linux, but it's kind of weird. And when you have that, you'll see this nice little display of all the things that you can use to open up or launch Python. So Anaconda comes with Spider, which is an IDE. It's very much, it kind of looks like RStudio if you're coming in from the R world. You have the option to open the Jupyter Notebook, and something pretty new is this thing called Jupyter Lab. So if you want, I'll be doing everything through Jupyter Lab. There's some benefits and some cool things that happen. It's pretty much the same thing as a notebook, except you have like multiple things on the screen at the same time. The nicest thing is like if you have multiple notebooks, you can actually have them. You can sort of have them displayed side by side. You can have a console on one side, stuff like that. So it's been pretty useful. If you can also use Jupyter Lab to preview like CSV files, something that the old Jupyter Notebook didn't know how to or couldn't do. So that's sort of useful. All right, one of these is the zip. All right. Other ways you can launch Python. So there's this thing called the Anaconda prompt. And if you wanted to launch the Jupyter Notebook, you would type in Jupyter, P-Y-T-R. You can type in Jupyter Notebook, or you can type in Jupyter Lab, and it'll do the same exact thing. If you want to launch Python, you can type in Python, and there's your Python prompt. Right. So, but yeah. So right now, what you should do is on the left-hand panel, navigate to that notebooks folder that you created. And up here on the top left, there's this plus button that you can use to create a new notebook. So let me do that from scratch for you guys. If you click that, you'll have the option of whether or not you want a Python 3 notebook. You can just open the console if you want. And this is a regular terminal, and you can also have a regular text file. So if you want to use the Jupyter Notebook or Jupyter Lab as a sort of here's my console, here's my .py file, copy and paste, type in one, copy and paste in the other, you can do that as well, and you can use the layout system to sort of split the screen that way. But for now, I'm going to be using the notebook. So what you should have is a screen that looks like this. So people in the back, can you see that? Or should I make it bigger? Yes, that looks terrible. How's that? Is that better? How's that? All right, that might be a little too much. All right, 250. Okay, cool. Believe. All right, cool. So let's get started. So this is a course about pandas, so we will have to load the pandas library. What you can do is, if you're new to all of this, Control-Enter will take whatever is written in the cell and execute it. Shift-Enter will execute the cell and also give you a new cell underneath. Right? And so the first thing we're going to do is import the library called Pandas. Python is great of a language as it is, doesn't, when you load it up, doesn't import everything known to man. Otherwise, it will just take forever to just launch Python. And so we have to say, like, hey, there's a specific library that we want to bring in and use its functions. Something that you might want to do is take a look at the Pandas version, especially if you're on a machine for work that isn't really updating things. There's been a bunch of changes since like 0.19, 0.21, so you want to be at least above 21, I would say. Otherwise, there are certain things that are slowly getting removed or deprecated or depreciated, and you just want to be mindful of that. All right, so let's load our first data set. So pandas is a library, and if we want to use the functions within this library, we have to use this period or dot notation to access things out of the library. So there's this function called read_CSV. And the way we use it is we say pandas, the library dot read CSV. The other thing about the notebook so the notebook system actually runs on something called IPython. And so if you have your cursor sort of in between a set of round brackets or in a function call, and you hit Shift-Tab, you'll get the signature back. This is something similar to using question mark and then the function name, but this is also really helpful. So the first thing read_CSV takes is a data set. So what we will do is, since we're in the notebook folder and we want to go one folder up and then into the data folder, we have to say .. for saying, hey, go one folder up and then the data folder. And then in this data folder, we have this data set called gapminder.tsv. This data set is kind of special in the sense that we're using a CSV reading function, but our data set is actually tab delimited, not comma delimited. And so we have to specify a delimiter. There's two ways you can specify delimiter. One is using sep equals, and the other one is actually using the parameter called delimiter equals. They're both exactly the same. One just requires less typing. And to tell pandas, hey, instead of commas, use a tab, we use this \t. So if you have like a semicolon delineated file, you can put a semicolon in there as well. All right. So if we run Shift-Enter to execute that line, you'll see that what pandas did was it took that tab delimited file and loaded it straight in. And it gave us that file or that data set back to us. So that's nice. We got a data set loaded in, but it's not particularly useful because we can't really do anything else with it. It just loaded it in and dumped it out. So what we want to do is actually assign this to a variable. So we can say DataFrame equals pandas read_CSV, and pretty much you can copy what you just typed. And now we have our data set. Instead of it just giving it back to us, it's saved as this variable called df that we can then use throughout the data cleaning process. Another thing that you'll see really often in working with Python libraries is this notation of import, this as notation. Yeah.
Hey, I'm sorry, I got stuck on step 0. I didn't get CD in the right directory. How do you CD once you're in these notebooks?
How do you CD? So the easiest way is to close the notebook in the left-hand panel, like go into the proper directory and then create a new one.
So I'm not in Jupyter Lab, I'm in Jupyter. So how do you do it in Jupyter?
How do you do it in the actual notebook? Let me just fire that up too. You see this, right? This version? So if you're pretty much this page right here is like that left-hand panel. So what you would want to do is like navigate to that folder that you want. And then on the top, go to new notebook Python 3.
You go in there somewhere, and then see that. Then I'll stop it.
What do you mean dot?
Should I create that right here?
So there's this folder at the very top. That's, yeah. All right, cool. right, so this notation of loading libraries in, instead of saying pandas dot read CSV, you're going to be using pandas a lot. You're probably going to end up typing pandas a whole bunch. So this notation just says, hey, I'm giving it an alias. So instead of typing pandas, I can just refer to it as pd dot, right? One thing you don't want to do is do something, you might see notation like this when you are working with older bits of code, is something that's along the lines of from pandas import all. You definitely don't want to do that. What that does is it loads all the functions into the global namespace. So it's useful in the sense that you don't have to type pandas dot or pd dot. But then if, for example, you have if, for example, there's like a mean function that pandas has, now it just overwrote the base mean function or a mean function that you wrote yourself. So you definitely don't want to do that. So if we take, whoops. So just to show you, we can do exactly the same thing as before. And we get the same exact result, right? So this pandas dot and pd dot do exactly the same thing. So once you have your first data set loaded, what do you want to do with this? There's a few things that you want to do. Something that really helped me when I first started working with pandas is you can use the built-in type function in Python. And sometimes things in pandas or when you start doing data transformations, it does not give you a data frame back. And so when you're assuming something's a data frame and you treat it as a data frame when it's really not a data frame, things can get a little wonky. So always run type if something's going wrong, just to make sure that the object that you have is what you are expecting. All right. So other things about this data frame. A data frame has this attribute called shape. So everything in Python is an object. Objects can do things, so they're called methods. They also have essentially attributes or things about them. So one of the things about them is the attribute called shape. And if we run df.shape, we get the number of rows and the number of columns in our data frame. An example of a method that this data frame has is this info method. So you can see that attributes don't have the round brackets after them, but the method does. And so info gives us a whole bunch of summary statistics. Well, it's not really summary statistics, but a bunch of information about our actual data frame. So it tells us the actual type. We have 1,704 entries. Here are all the column names of our data frame. This is the number of non-missing values in our data frame. And on the right-hand side is the actual data type. So if you see in Pandas the word object, typically that is probably a string. It's how strings are represented in Python or in Pandas. But it doesn't have to be a string. You can actually put some arbitrary other Python class object in there as well. So something I've done recently was I pretty much had a data frame where one of the columns was like a request object. And then I just pretty much had the other columns being like metadata for where did I get this request thing from? What was the URL I pulled from, et cetera, et cetera. So it does not have to be a string, but typically if you are working or just loaded up a data set, object will refer to a string. And down here, it'll tell you how much space the data frame is taking up in memory. It's not the exact amount. It's just a really quick estimate. There are ways, I think, in info. You can say memory usage. I think there is a way to specify if you actually need the true value, but usually that estimate is good enough. And just to show the difference between attributes and methods, if you, for example, forget that shape is an attribute instead of a method, and you put in round brackets, you'll get an error because shape actually returns back a tuple, number of rows, number of columns. And so it's going to be like, hey, I don't know how to call a tuple. So that's what that error message is. All right. So that's some of the basic things of when you just loaded up a data set, you're probably going to want to run this just to see what's going on. But if you want to see if something got loaded up properly, you're going to end up wanting to use this method called head. And all head is doing is it prints out the first 5 rows of our data frame. The analogous, the other way, there's this method called tail, and it gets you the last 5 rows of your data frame. Typically, you'll probably use this if you just want to make sure that like your column names got loaded up properly. But there are pretty much 3 different components of a data frame. There is what you have here, your column names. You'll see the numbering system on the left that is called the index. And then there's the actual body or data part of our data frame. So if you ever need to, you can access those 3 components separately. So if you just want the column names, it's df.columns to get all of your column names. If you want the index, it's df.index, and you'll see that the index right now is really just a range object that starts from 0, ends at 1,704 on 1-step increments. For the most part, if you're just starting out, this is probably what you're going to end up seeing. But if you end up working with time series data, you'll see a lot of people convert the date column into an index, and it just sort of makes slicing out or filtering out your data a little bit easier. But this is how you would get access to that part. If you're coming from other languages, you can think of the index as the row name, for example. And it does not have to be unique. Neither do your columns. Your columns don't have to be unique either. And if you want the actual body or the NumPy array representation of your data frame, it's df.values. And you'll see that in a little bit when we start working, when we see how Pandas fits in with some of the other libraries. Occasionally, if a library only understands NumPy arrays as inputs, you're probably going to have to run like df.values to pass in the array version instead of the actual data frame version. And the reason why they do that is just, I think like a couple of years ago, it just made like maintenance easier. They just didn't have to deal with like a data frame object, like just give them a NumPy array. And if you didn't really need to run df.info and you really just cared about like, hey, what got loaded? So typically, for example, if you have a column that you expect is all numeric, and for example, someone typed in that column like missing for missing, that column, because each column has to have the same data type, it will all get converted into a string. So if you do run df.dtypes to get a look at for each column what the actual data type is, it's a good way to spot check to make sure that you didn't have like any bad values floating around in that particular column. All right. Cool. All right, so subsetting columns. Oh, so object is typically what Pandas is going to load strings into. So like missing as like a quoted string. That's pretty much what object is going to be. Int 64 is a 64-bit integer, so it's just telling you that this is a value that doesn't have a decimal point in it. In our data set, this is, I should have explained this data set. So this is a data set for each country for each year, what the average life expectancy, population, and GDP per capita is, and where that country exists. So life expectancy would be some calculated value, so it's probably going to have a decimal point, so it's going to be encoded as a floating point number. And there are a bunch of other types as well. These data types all come from the NumPy library. So if you really needed to say, for example, int 64, like year is only ever going to be 4 digits, so I can probably get away with like a smaller integer value to save space. You would look up how NumPy stores, or how NumPy refers to their types, and that's where you get those data types. Right. So subsetting columns. So Pandas, a data frame object, you can almost think of as this isn't really a true statement, but think of it as like a Python list where each column is a list object. Technically, a Python or a Pandas data frame object, each column is a Pandas series. And a series you can think of as an extension of a NumPy array. So that's why each column has to have the same data type, because NumPy arrays pretty much have to have the same data type. So how do we get individual columns out? We use the square bracket notation. So this is how Pandas or Python uses subsetting. And if we put in a single quoted column name, that's how we would get an individual column. So if we wanted the country column, we can say df in bracket country, and we'll get that entire column back. So if we look at country, we can see, if we look at the data type, if we use the single square bracket and put in country as a string, you'll see that what gets returned back is a series. So if you use this type of notation, know that if you pass in one column, you get back the actual series object. If you're programming for a larger group of people or for a library and you need these things to have a consistent data type, what you can do is pass in a list of column names. So this double square bracket notation, the outermost notation is going to say, hey, I'm going to be subsetting something. And the inner bracket is pretty much saying, hey, I'm going to be subsetting multiple things. And the way you specify multiple things in Python is a Python list. So the inner set of square brackets is a Python list, and the outer one is just saying, hey, I'm subsetting. So you can subset based off of a single value or a single column. And if we look at the type of that, you'll see that that's how we get back a data frame. So if you're working with larger pipelines or you're writing your own function and you want to make sure that your data type is always going to be the same whether or not someone passes in one column or two columns, you'll probably end up using this double square bracket notation. So if we look at our data frame, another thing that you might end up doing when you first load up a data set, so in read CSV, it's a pretty big function if you look at the function signature. There are ways to only select certain columns during the reading process. But if, for example, you loaded up your data set and then you're pretty much saying, hey, I actually don't need that column, or that column is completely useless because it's really just a set of missing values, there are ways that you can delete or remove columns out of your data frame. So one thing that you can do is use the built-in del or delete. I don't know if this is statement in Python. So if we wanted to delete the country data frame, the country column, we would say del df and then just give in like the column that we wanted to delete. And you can see that it sort of works in place. We didn't have to assign data frame back. We can just say, hey, just delete this column, and it just deleted it for us. All right, so because I actually needed that column, we'll go back and yeah, so if you wanted to delete multiple, so in here, you would put in square bracket and multiple columns. So let me show that to you. So if you wanted to delete multiple, you have to treat it as you're going to be selecting multiple columns. And what is it? Uh-oh. Did I spell it wrong? Uh-oh. Oh, is it this way? I usually don't delete columns this way. So if you want to stay in the pandas world, which is usually what I do, there is a method called drop. This is what I would suggest. And in here, you can pass in multiple labels as a list. So we can say, So the trick about drop is by default, it will start dropping on the, on the row axis. So if you run in Shift Tab, you'll see that there is this parameter called axis, and it's by default set to 0. If you look in here, 0 refers to dropping things by the index or by the row, or you can pass in 1 or the string columns to drop things on a column basis. It used to be that you only were able to specify 0 or 1, and then in the newer versions of Pandas, you can actually put in the string index or columns just to make your code a little bit more readable. Yay, right? So that's usually how I end up dropping columns, is using this drop method. A lot of the Pandas functions have this parameter called inPlace. By default, it's going to be set to true. That's usually to protect you from yourself. Because if you see when I ran this function, it returned back a new data frame without the missing columns. But if I looked at the actual data frame, it never really overwrote. It didn't do anything. So if you wanted that drop to persist, you would have to either reassign it back to the variable or set that in place argument to true. And I am going to need that back. All right. So that's about subsetting columns. Pretty simple in the sense of what you're really doing is using the square bracket to subset, and then in there, if you need multiple, put in a Python list of which columns you want. So the next thing I want to talk about is how do we subset rows. It's a little bit different. We have to use this accessor. So there are 3 ways that Pandas allows you to filter or subset rows. 2 of them are the ways that you should do it, and one of them is if you try to run it, it will just scream at you and still do something. So I'll show you all 3 of them. So there's the first way to subset rows is using this accessor called loc, L-O-C, which is for, I think, location is what it actually stands for. And in here, you can put in the value of the index. So here, LOC, when you put in 0, it is looking in that index or that row name, essentially. Hold on, let me. It is looking at this index and seeing which one matches what you passed in. So it's not taking the first element. It is matching which one of those rows match this thing that you passed in. In this case, it is the integer 0. Right? So that's a pretty subtle difference. When you start concatenating data sets, this becomes a thing. This is something you want to think about, because if you have multiple data sets that have the same index and you just stack them right on top of one another, you'll have 2 versions of 0. So when you run LOC 0, you'll get 2 rows back, not the first row back. So that's the subtle difference there. So just another example, Python, when you put in negative values, allow you to start subsetting things from the back of a list. So if we put in LOC -1, it's going to give us an error because -1 is not a value in the index, right? So it's not actually saying, it's not selecting things in a positional, in an index sense, as if you were just selecting things out of a list. It's really essentially just doing like some kind of string matching. Yeah. Oh, are you saying that you ran that? Oh, yeah. So that's just saying that, like, when you run this, it's giving you square brackets? All right, cool. There we go. Square brackets. Sorry. Cool. Yeah, my next guess was like, do you have a space there? So if you wanted to select multiple rows, you do the same thing as you would do with lists. With columns, you put in another set of square brackets, and you can get, in this example, the row that has the index 0 and the row that has the index 1, right? So again, this is not the same as position 0 or actual index 0 and index 1. But sometimes you actually do want to refer to rows by its like absolute position. For example, if you have multiple rows with the same index and you really care about like, hey, I actually mean like 0 as like the first row. The other way you can subset things is using iloc, so the I for index. So now if we say something like 0, this is the actual first row of our data frame. So it doesn't matter what that label is. It could be like 42. It's really just giving you that first row in your data set. So it's essentially running, oh, that's not good. Another way you can think about it is it's essentially running head, but just giving you the first element, right? And so because this is because this is more or less like filtering or pulling things out by its index position, if you pass in something like -1, this time this will work, right? Because it's actually going from the back of your data frame and pulling index -1 versus the piece of text -1. So the question is, which one's more common? It will depend on what you really need it for. I personally, in general, I'll just say like in general, I try not to write my code to use these positional arguments, just because when I go back to it, like, especially if you're filtering columns, like, hey, I'm just going to use the first column of my data set. It's like, if I go back to it, typically I'm going to have to run df.columns to see what the first column was to begin with. So I generally try to use the actual like named versions of things if I can. There's certain things like if you're working from Pandas to scikit-learn, a lot of times you'll set up your data frame such that the first column is your response variable, like the variable that you're trying to measure, and then everything else is your predictors, in which case you'll see a lot of people just says like, hey, the first column goes into as my y, and then index 1 : becomes my x. So you'll see stuff like that, and that's just useful just because you don't have to type in all your parameters that way. But if you're processing data, I would say try to do things by name, but that's just a rule that could be very easily broken. So I showed you how to subset columns and rows. One thing that is useful or more useful is subsetting both columns and rows at the same time. And the way you do that is you're using LOC. So in LOC, you can think of it as, if you worked in other data science languages, I would say like R or anything that has like a matrix object or a data frame object, this notation is going to be pretty much the same. So you can think of the square bracket on the outside is how we're going to be selecting things. There's this comma, so we can select things based off of 2 different axes. The thing to the left of the comma is how we're going to be selecting the rows. So if we use the Python slicing notation, the colon notation to say, hey, we're going to be selecting all of the rows. The thing to the right of the comma is how we will select the columns. Right. So if we wanted all of the rows, but only wanted the year and population column, we can use this .loc notation as well. So this is sort of redundant. If this is what you want, you would just end up usually going back to the notation I showed you in the beginning. Like, you don't need to use .loc. But the reason for this is you can use this notation for Boolean subsetting. And just to complete the example, if we do something like iloc, this won't work, right? Because iloc takes index positions, and year is not an index position. It's not like the first column or the column of index 0, right? So if we wanted year and pop, I believe it's 2, 4. So that's just, again, another difference between loc and iloc. One really is just looking at the index position, and the other is looking at like the named position, or the name. So why do you want to use loc in that notation? It's really for Boolean subsetting. So for example, if we wanted all of the, we wanted to filter our data sets such that we're only looking at the United States. So how will we do that? So we're going to be using loc to filter on the rows. How do we actually filter on the rows? Well, we want to say, hey, in our data frame, we're looking at our country column, and we want those values to match United States. Right. So in here, this df country, so that first part is how we selected the country column. And the second part is saying, hey, for each one of those country values, note that we don't have to write a for loop for this. Does it equal or does it match United States? So if we look at this, down here, all we get is this. It's really a Pandas series object. And we get, we get a series of true or false values, right? So we can use this as what's known as a mask to mask our data frame and only return the values that return true. Oh, yeah. So the question is like, there's different ways of specifying columns. I'll talk about that in a bit. Yeah. And another thing that sort of took me a while, I always make this mistake as well. In Pandas, if you wanted multiple things, you'll say and or. But the way this works is really using bitwise comparison. So you can't use that. You have to use the ampersand or pipe for the and or operator. So if, for example, you wanted country in the United States, but also the year to be 1982, you would think that this is how you would do it. But if you are trying to put in together multiple Boolean conditions, because it is a bitwise operation, the individual components you have to wrap around in a set of round brackets. Just so it knows that's one thing, and then the other thing is another thing. You'll see pretty often, as a convenience, I would say, like I showed you, you can pull out columns by using square bracket colon notation, square bracket and then a string. A lot of times you'll also see people just forego the whole square bracket and string and use dot column name directly to access the column. That is fine. You just have to know that this dot in Python is really, hey, I'm looking in this object for that, in this case, attribute, right? And so in this case, it makes sense. Year is a column, and that's the way it's set up. But for example, if we had a column called shape, and you ended up doing this, you don't get the shape column back. You get the number of rows and columns back, right? So if you're in like the whole data science pipeline, and you know that's not going to be a case, or if you are not writing a function for the general public, you can get away with this. But if you are writing like a module, for example, you would definitely start using square brackets, because you will never have like this thing that returns back like the shape attribute instead of the shape column. Right? But yeah, I totally use the dot notation just because it saves you like three characters on the keyboard, or 4 if you're hitting shift, right? So, all right. So our last topic for the intro portion. So Pandas is pretty powerful in that it really does, like, if you are coming from like spreadsheet world, everything that you do there can totally be done here, right? So one of the things that if you got a somewhat clean data set and you just want to start figuring out some general statistics, so what's one question we can ask for this data set? One question we could ask is like, hey, how does the average life expectancy change across each year, right? Like, given this data set's pretty very Hans Gosling, I guess. So the way we would do that is it called group by in Excel? I don't even remember. It's been so long. Say again? That sounds right, yeah. Aggregate, something like that. So we can do group by statements in Pandas as well. I'm not going to go too much into how group by works, but this is definitely enough for just a touch of it. So if, for example, the question was like, for each year, what is the average life expectancy, right? So we need to filter our data set by each year and then pull out the average life expectancy column and then calculate the mean. So the first step we need to do is break up our data set by year. So we can say, like, for each year, we will group by year. If we run this, you'll see that what we get back is a data frame group by object. Essentially, it didn't really do anything yet. It just says, like, hey, anything else that you do, know to do this by year as a grouping variable. So in your head, just think of this as a regular data frame, and we will treat it as a regular data frame. So if we wanted the life expectancy column, we will pull out, using the square bracket notation, life expectancy. And again, we haven't really performed the calculation. It just knows that, hey, we have everything grouped by year, and we have the life expectancy column. Because so much of Pandas is built on top of NumPy, these objects already have a lot of your basic summary statistics. So we can calculate mean, for example. The more verbose way, if you wanted, for example, to put in your own custom function, or ag, you can put in your own custom function here, right? So just in general, so group by, it's just a way to essentially break up your data set. But there's different ways that you can do with those broken pieces, right? So if you work on distributed systems, this is probably very familiar. How do we break up our data set into years so each separate machine gets its own data set of just year, calculate the mean, and just return the value back? So this is a grouped data frame. So think of it as a data frame, but it just understands if you perform a calculation.
You are creating your own function, you need to set it as the input as data frame.
Yes, yeah. Yeah, this part here needs to be a data frame. So yeah. So this is just a built-in convenience thing. So if I really wanted, oh man. Yeah, so this is any function that you want. If it's completely custom, you have to write it in a special way. It has to be like a vectorized function, which we'll cover at the very, very end. But just in general, so ag or aggregate, pretty much that notation is we take a bunch of values, so like a whole column of values, and the thing to keep in mind is aggregate will only return one scalar value back, right? Like a mean takes in a bunch of things and gives you one number back, right? So that's when you use ag. There's other versions of group by. For example, if you take a bunch of values in, you get the same number of values out. For example, if you're centering or scaling your data or taking a z-score, that is called transformation. So you'll use .transform if you're trying to do a z-score by group. And then the other way is called filter, which I don't know why anyone would ever use, but that's a bunch of values in and number of values or less back out. So like filtering takes in a bunch of stuff and gives you some number back that's between 0 and the number of values you gave it. But typically when you're doing group bys, you're probably running aggregations because that's how most summary statistics are being calculated. All right. So let's make this example a little bit more complicated. So let's say we don't care about year or just year. We care about like how does year and continent change. I wonder why I picked those. So just like with columns, if we wanted to put multiple things, we wrap it around a Python list. So we use square brackets. And if we wanted more than just life expectancy, we wanted life expectancy and GDP per cap. We would wrap those bits around square brackets. So we pass in a Python list. And you can see this is something a little different. You can see it did its job. Like for every year in continent, we have the average life expectancy GDP per cap. But the first thing that you'll notice, especially if you're using IPython or the notebook system, is this data frame got printed out kind of funny. So this is, I'm not going to cover this too much, but this is when you see some weird spacing going on around here, you have a multi-index is what's going on. So typically, especially if you're first starting out, and I do this all the time just because I don't want to deal with multi-indices, what you might want to do is just say reset index and get you a regular flat data frame back, right? Because typically if you pass in a multi-index data frame into other things, or you treat it like a regular data frame, and you're like, hey, I want the year column, and it's like, well, that's not really a column, it's actually an index, like a row. So it looks different as a prompt to say, hey, it's actually different. And for the most part, I just say reset index just so I want something flat back. All right. Cool. So that is our first bit of just loading up your first data set, looking around, doing something. We'll take a break until 9:05. And then in the meantime, so you guys can get coffee if you want, stretch your legs. All right, so we're going to load the tips data set. So the way we do that is Seaborn, the plotting library, has a bunch of these data sets in there. And I'll just show you this part. So just like how Pandas has a read CSV function that we looked at, Seaborn has this function called load dataset. So we're loading the tips dataset. Right. So for the next 10 minutes, if you want to work on this problem, get coffee, etc., filter this. I don't know what's going on. What's going on? Uh-oh. I'm pretty sure I spelled something wrong. Or not. No. So the data set comes from the library. So it's like essentially like a CSV that's already like in there. Oh boy, URL open error. Is anyone else having this problem? I wonder if that error message has something to do with it. Oh, it's because my. Are you guys? Hold on. Let's see if it's an internet problem. Oh boy. Say again? Yeah.
The internet still isn't connected fully. If you look at the queue cycle, so.
Yeah. Okay. Maybe it's an internet thing, which I didn't know. I really hope this works. We actually use this data set like throughout. Hey, look, it is the internet. All right, cool. Okay. Make sure your internet is connected, apparently. But yeah, so filter based off of some value of gender and total amount, right? Like, let's say greater than $10. I don't think so. So the tips data set is super common. So I would say as a backup, I'm pretty sure you can download the raw CSV. Yeah. Oh, look, it's right here. Um, yeah. So if it's not working, I guess I can show you how you would download stuff straight from GitHub. So if you look up tips Seaborn CSV, it'll give you the link to the actual CSV page on GitHub. If you ever want to download a single file on GitHub, which is useful for data sets, when you click on, so for example, here are all of the data sets from Seaborn. You would think that if you click on tips.csv, you'll have access and you can just download it. The actual trick is to click raw and then right-click save as. Otherwise, what you end up getting is the actual HTML of the page and not the actual CSV of the page. So, oh. Yeah, if you're loading it from a CSV, use the read CSV function, yeah. Oh, the how to read the Seaborn data?
Because I had to install it, I didn't have it, so I kind of got.
Oh, right here.
Yeah.
Could you scroll back to the URL?
That one?
Yeah.
All right. I want to say the easiest way to get to it is Google Seaborn tips CSV, and it's,
I got it.
and Yeah, you can use the read CSV functions. Make sure it's like in the data folder, so it kind of looks the same as before. Yeah. Hi. Can you tell the AV guy that? Is this on? Is this on? Is this back on? Yes, no? All right, cool. We're good. All right. All right. So it's 9:05. We'll get back started again. There we go. Hello. All right. So apparently, like when you run load dataset, it actually makes a request call. So if the internet isn't working for you, you can download the tips dataset, which you'll actually need. If you're going to be doing it this way, also look for Titanic because we'll be working with that one eventually as well. But so for the actual solution, so the question was like, hey, take the tips dataset, filter it by some value of gender or sex, and filter something by total bill, right? So this is something that you'll probably end up doing, looking for bad values, or all of a sudden you're like looking at the data type, and all of a sudden you're like, what is going on? Why is this column not like an integer or something? And so you'll be doing this kind of Boolean subsetting or filtering pretty often. So we'll be using LOC since we'll be referring to things by its actual name. So LOC, again, remember that we have a set of square brackets to do the actual subsetting. We'll be subsetting on multiple conditions. In this case, we're looking for sex and some total bill amount, so we have this AND operator. Each Boolean condition we wrap around in a set of round brackets. So the first one is tips, looking at the sex column, so we can use .sex or bracket string sex is equal to female or is female. And then the second one is total bill greater than 10, for example. And you'll see that what you get back is a data frame that met that criteria. if, for example, if you wanted to save this, again, it just gave you the data frame back. So if you wanted to save this as a result, just know that you have to save it to an actual variable to work with. Right. So I will be calling this intro. So if you want to rename your notebooks, you can right-click, go to rename notebook, and you can rename your notebook that way. So I am going to create another notebook, just so it breaks up the topics a little easier. Does this work? Yeah, it does work. Some bash commands actually do work. Is pwd a Windows command? Yes. Yeah, okay. So you can use like somewhat basic bash commands in the Jupyter cell. So if you are ever curious where your current working directory is, you can type in pwd and it'll give you the bash pwd. ls will essentially just run dir for you on Windows. So if you're just trying to browse like what is going on, where am I, that ends up being kind of helpful. All right, because this is a new notebook, the state or the variables created in our previous notebook don't really carry over into the current notebook, which is a good thing. So stuff like importing pandas, we have to redo again. And so in this section, I'll pretty much just cover like how do you create these data frame or series objects by hand. Typically, you'll have data coming in from some other means or some other block of code that you're writing. And if you want it into a data frame object, this is how you would do it. So to create a series, or think of it as a vector or one column of your data frame, we run pd.series with a capital S to create our series. And in here, we give it some kind of iterable or container. So here I'm going to be using a Python list, and we can say pizza and 42. And you can see that when we do this, so this is a mixed type. So even though that Python lists could be arbitrary types in there, when we pass it into a series, you can see that its D type is now an object. And for the most part, when you see object, think strings, but it can be really anything in Python. And so this is really just to show you that if you have a mixed type and you put it into a series, it's always going to coerce it into something that fits all of the types in there. So most of the time, that's going to be a object or a string. So series, just like data frames, they can have an index as well. So we can do something like index equals, the first thing is a food item, and the second thing is a number. And you can see instead of this 0 and 1, oh, I spelled food wrong. Instead of the 0 and 1 on the left-hand side, we now have food and number, right? So this is where loc and iloc come into play. So we can say series.loc, and we can now call it by food. So this, you can almost think of this as like how you work with dictionaries. The index becomes a key. Just the index doesn't have to be unique, right? And so that's one example of like using loc and iloc, where if you wanted the first element, loc will call things by its name, and iloc will call things by its actual position. All right. So that's how we create series. How do we actually go and create data frames? So a data frame is pretty much, the way we create a data frame is pretty much very similar to a series. Instead of series, we use data frame where the D and the F are capitalized. I think I made the screen smaller. All right, so that should be a little better. Because the data frame really has two bits of information, like what is the column name and what are the values that go into a column. Usually when you have that type of data structure, you end up using a Python dictionary. I believe there are other ways of doing this, creating data frames, but I usually end up with passing in Python dictionaries. So here you can pass in a Python dictionary where the key is the name, and the value are the values that go into that column. So we can say Franklin and right. So we will create one column called name, and the values are going to be Franklin and Gossett, and then another one called job. The capitalization doesn't matter, but you really should be consistent. And so job, we'll see. This is chem and stats. Right. So that's how we will end up creating a data frame. So just a little bit about Python dictionary. So for the most part, we've been seeing square brackets for Python lists. If you see squiggly brackets, that's how Python defines a dictionary. Think of dictionaries as like book dictionary, where like the key is the name or the word, so name, and then here's like the actual definition or the values. So in this dictionary, the key becomes the column name, so we have name and job as the keys, and then the values end up being those values in each row or in each column. All right. All right, so instead of making you guys type up a whole bunch of scientists and their names, I sort of just hand created one called scientist.csv. I pretty much just took all of this information from Wikipedia. So if you have the occupation, I can only just put one, or I only put one occupation in there, so that's why it's not totally accurate. Whoops, sorry. Yeah, whoops. Yeah, that's important. I forget how zoomed in this is. I actually need the clock, so. All right, so I showed you before like some of the basic things like looking at info, dtype, shape of a data frame when you first load it in. If you end up looking at, if you end up wanting to look at like more descriptive statistics like mean, standard deviation, et cetera, there's a lot of that stuff is already built in for you. So we have this age column, which I think is capital A. Hold on. So capital A for age. We can look at .describe, and it'll give us a whole bunch of statistics or just summary statistics if our value or the column is numeric. Other things, just so you know. So here's the age column, or a series, or sometimes I call them vectors because that's how people refer to these things in R. So I have a vector or a series of age. Things in Python or in Pandas, there's some, and also in Numpy, it's called broadcasting. And so if, for example, you do something like age plus age, what will end up happening is this element-wise addition, right? So you don't have to write a for loop that says like for each element in this and also each element that like add the index zeros together, add the index ones together, et cetera, right? So it understands when you give it two vectors or two series, and if the series are the same length, it knows to operate element-wise. So you can do stuff like addition, multiplication, like all your basic operations. It knows to operate element-wise if they're numbers, right? So you don't have to write a for loop to do stuff like this. If, for example, you pass in a scalar, it will repeat or recycle the scalar across all of the elements in your vector, right? And so, yeah, so that's actually the next point. If you wanted to make a calculation and then assign it as a new column, the way you create a new column or a single new column is you pretty much pretend that the column always existed, is the way I think about it. So we can pretend that age doubled exists as a column, and we can pass in age times 2. And then if you want, you can look at your column or you look at your data frame, you'll notice that it created a new column of that calculation that you just made. So I showed you loc, iloc, shape. Those were the attributes of a data frame. There was like info and describe as methods of this data frame or data frame has. How do you actually try to keep track, or how do you keep track or remember any of this? So if you Google Pandas DataFrame, this is actually pretty good because I'm not signed in or anything. The first piece of, or the Google search result is DataFrame, Pandas DataFrame from the actual Pandas documentation. And you can see here, this is how we created our data frame object, right? So the first thing is like, hey, you can pass in a dictionary, you can pass in an ND array, some iterable or another data frame to convert into a data frame. But if we scroll down a little bit, you get a table of all the various attributes. Let me make this bigger. All the various attributes a data frame can have, right? So we looked at loc, we looked at iloc, it's somewhere in here, iloc. The third way that I showed you that I said pretty much don't use is one called ix or ix. The reason why you don't use ix is because one, it's deprecated, and the second one is it allows you to filter on the index label or position. And I think it looks at the label first, and if the label doesn't exist, it filters by position. And so that's terrifying. You should just specify like what are you actually trying to do. So that's why it's just like not there anymore, or you really shouldn't be using it. If you try to use ix, it'll just throw this big giant red block of text saying that like please use something else. Other things in here, so we showed you shape. T, if you wanted to just do a transpose, it's just the dot capital T, just to flip the column names and rows. But down here are all the bunch of methods that a data frame can do, right? So like something that I didn't really show you, but you can do cumulative sums across a column, right? It's all built in. The thing to keep in mind is Pandas was, when Wes McKinley wrote Pandas, he was working at a hedge fund. So a lot of this stuff that work with time series and like data that deal with money, it's probably already built in. So there's a lot of cool stuff in here. One question I get a whole bunch is like, hey, I really like R's piping syntax. It's like so much cooler than Python. But I was like, dplyr and all those other R libraries are actually just built into Pandas. It's like instead of the percent greater than percent carpal tunnel inducing syntax, you just say dot, right? So there's a bunch of stuff in here. One thing I didn't show you, which I'll just point to right now, if you say _, there's a bunch of ways you can write out your data sets. So you can actually have a data frame go into your clipboard, and then you can paste it into Excel or something. I think the other way goes, I think there's a way to go from clipboard to data frame as well, but there's one called toCSV. We'll write a few CSVs later on. You can actually write the thing to an Excel file. So if you, I think you can actually specify like a sheet name, et cetera, stuff like that. You have to do some installing, but if you do work with, like me, like Python and R, and if you're jumping between two languages and you need to write out data to be read into another, Feather is the data structure type that was built to transfer data from Python to R efficiently, very efficiently, without having to read out a CSV and then load it back in. If your data sets are small, it's probably not going to matter, but if they get bigger, then you don't want to end up waiting 30 seconds to write out and read in to another language. You can also, if you have database connections, you can just say, take this data frame, dump it to that Excel, dump it to that database thing. You don't have to create the table. I think you have to create the table to begin with, I think. I don't remember off the top of my head, but you don't have to write a for loop for each row. Just it will do that for you. Right. So this is the data frame, the official data frame documentation. there's the same page for series, so if you're curious of what a series can do, you can Google that as well. All right. All right, so I totally also, because of this computer thing, forgot to tell you guys about housekeeping notes. But the next thing that's sort of relevant is snacks will be at 10:15, so I'll make sure you guys will have snacks. We'll have a break right before then. Is it? Oh. Did you guys get snacks? uh, oh man, I was based off of this clock. Okay, there will be snacks later. If somebody wants to like run out the door and tell me if I've made a horrible mistake. That's interesting. Okay. Nope, I totally am reading what I'm saying. It's just this clock is wrong. Yeah. All right. All right. So the next thing I want to talk about is something that, if you can understand this, I think you pretty much would have understand everything that you'd really would need to start your journey learning everything on your own. And that's this concept of like tidy data, or like when you get a data set, what are some of the first things you want to think about in terms of like how do you like quote unquote clean this thing, right? So this comes from Hadley Wickham in the R World, and I think this paper is pretty old now, 2007. I don't know when he wrote this thing. But anyway, I'll make a link to this. There's already a link to this in like the pre-reading for the course, which you didn't really have to read, but it's there. So this paper talks about different ways data come to you, or different ways data gets stored, right? So the first example is, okay, let's say we have a data set for a given treatment, 2 types of treatment, and people, and some value. This data set makes sense. You can compare for a given person. Is there a difference between treatment A and treatment B? You can visually see this. If you're like someone who's collecting and entering data, this is probably one way you'll enter data into a spreadsheet, right? Because it makes sense. But he also says like, hey, we can also transpose this thing, and you pretty much have the same information encoded, but it looks different, and we need like sort of better words to describe like what we mean by like a good clean data set. And he makes the case in this paper that like, hey, when we as data analysts, when we actually need to work with data, because eventually you get a data set, you want to fit a model, make a plot or something, he's going to say like, hey, this is the actual data format that you want to aim for, which might look weird because now you don't have the nice ability to compare A and B like across a row. But if you think about it from like what you plan on doing with your data, you plan on fitting a model. So for example, you want to say, this is like a terrible thing you would never do, but like for a given person, what is their result, right? So you want a column of names that you want to put into your model, and then like a column of results that you want to put in your model. Or you can say like, hey, how does treatment affect result, right? So you need a column that has different treatments and a column of its different results. And so down here, he says like, okay, so here's the definition of like a clean and tidy data set. Is each variable forms a column, each observation forms a row, and then the last bit is how you would store data, but each type of observational unit forms a table. And I'll show you what that means towards the end of this block. So if we go back to this data set, what does that mean? So each variable forms a column. So we have a name column, a treatment column, and a result column. And in each observation, so for a given person and a treatment, we have a result. That is a row of data, right? So that is, compare it to the previous examples. For example, here we have treatment A and treatment B, which are variables. It should be, again, if you compare it to the tidy solution, treatment A is not a variable itself. The variable is really treatment, and it's type A or type B, right? Each row is not an individual, it's not one observation. For a given person, we have 2 readings, right? So that's what makes this not tidy. But the benefit, and I'll show you guys in a bit how we can deal with this in code, is if you are inputting data, this is probably the way you'll input data because it's easy, and it's probably how you're getting papers, and it's how you can pretty much quickly spot check your work. And this tidy form is what you will want to clean your data into. And the benefit of getting it into this tidy form is pretty easy to get it back into the original form that you had it in, right? So if you're pretty used to like looking at spreadsheet stuff, like you can do a pivot table and then you just get the exact same result back from before. So this is the target that we're going to go for. And in this paper, he also talks about the process of getting to a clean data set. You pretty much have like these are like the 5 most common problems, and this is and usually along the way, usually as you're cleaning your data sets, you'll encounter one of these, or at least one of these problems, and we'll just show you how you deal with each one of these cases. So the first one is column headers are values. Column headers are values, not variable names. So that's the same problem that we had in our treatment thing. The column names are actual values. It's treatment A, treatment B. It's not actually in a column. So how do we go and fix that? So that's the first thing we're going to cover. So we are in a new notebook, so we have to load Pandas again. And the first part we're going to cover is columns. I totally misspoke because words are hard. Columns containing values, not variables, is what I meant to say, and I don't think I actually said that. So we'll be reading another data set. So here we'll be reading in data from the Pew Research Center. We're essentially going over like the paper is what we're doing. I swap out one of the data sets. I also, when I was going through the whole data science tract, this paper and this concept is like my starting point from jumping between R and Python, because all of the stuff that you learn here pretty much transfer over, and if you can get the sense of like how you can process data, the syntax ends up being like not as scary, because you already know like what to look for or how to do things. So here is a data set. For a given religion and income bracket, we have the number of people. And so you can see here what when you get a data set, instead of just like start typing things, I literally will take out a blank sheet of paper and draw out what I expect, right? So what I would expect is I would want a column for religion, a column for income bracket, and a column for count, right? That's what my final data set wants to be. And so how do we go from that in this data set? Well, so in here, there is this nice function or method called melt. It's called melt because when Wes wrote this in Python, it was, you'll hear Hadley Wickham's name a lot because this was a lot of the inspiration for Pandas came from him, but there was a package in the R world called reshape2 that had a function called melt that does this behavior. So what we want to do is take these columns that I have selected, and we sort of want to collapse or melt or make longer each one of those column names. We want them to be a row in our data frame, right? So that is what we're doing for melt. So if we look at melt, so if we hit Shift-Tab to look at the function signature, one of the parameter is ID vars, and the other one is value vars. So ID vars refers to what are the columns in your data frame that you don't want to touch, like just leave it alone. And in our case, our ID vars, the column that we don't want to touch is religion. Since it's just one value, you can leave it not in a list, but I'm just going to put it in a list just so you know that you can actually have multiple columns that you don't want to touch. The other column, the other parameter is called value vars. So this is the columns that you want to turn into rows. And the function is written in such a way that if you specify ID vars and don't specify value vars, it just assumes the rest of the columns. Or if you specify value vars instead of ID vars, it'll just assume the other columns not specified are going to be held static. And I'll show you what that means in a bit. And that's because I spelled things wrong. Did I spell it wrong? PD melt. Oh, whoops. Pew. All right. In the somewhat newer versions, oh, actually, let me just talk about the results. So we specify ID vars. So religion was a column that stayed as religion. All of the other column names, so those were the individual income brackets, now became this variable or this column called variable. And then the body of the table became another column called value. Right? So you can see like now we have something that's like Catholic under 10K 418, right? So if we go to Catholic under 10K, this value here is now specified as a row in our data frame, right? And this is good because if you think about it, like what do you plan on doing with this data set? One question could be like, hey, for a given variable, like predict the counts that we have in our data set. So we need a variable column and a value column. In the newer versions of Pandas, they sort of made the syntax a little bit more consistent, so you can also keep doing this dot chaining. So you can say dataframe dot melt instead of PD dot melt and pass in a data frame. If you look at the source code, one just passes values into the other. So right, so we can get the same exact results that way. One other thing, if you want to start thinking about like what your data set looks like at the very end, the other two columns or parameters that we didn't look at was value name and so var name and value name. By default, we have columns called variable and value, so you can actually pass in what you want those things labeled. So if we wanted var name to be income and value name to be count, that's how we would create a data frame that's tidy and also have the correct column names that we want. Right. And you'll notice when I ran this, it really just saved this out or just spit this data frame out back to us. So if we wanted to, we can say pew tidy, give it a new value. And you can continue processing your data that way. All right. So there's another data set. Read CSV. All right, so there's another data set from Billboard. And so this is for a given year, artist, track time, and date. And for some week from 1 to 72, what was its actual Billboard ranking of a particular track, right? And you can see here, this is really the same problem that we had in the Pew data set, except it's just, we just have more columns to work with, right? So when you see something like this, again, this is something that when you are working with data or inputting data, this is probably how you'll store it. It's way easier for a given song just to look across and input track information. But if your question was like, hey, for a given week, a song came into, I don't know, existence or listing, like what was its actual rating? Like if that's the analysis you wanted to do, you wouldn't be able to do that in the in this data set the way it's shaped right now, right? So we want the week from 1 to 72 to become individual rows. So that's a melt function. The other mnemonic that you can think about, so this is there's this notion of like long and wide data. Long literally means like there's a lot of rows compared to whatever you were coming from. So we want to take these weeks and turn them into rows, so it'll end up becoming long data. And the reason why it's called melt is you can think of like when you are melting things, that things become long, which is exactly the reason why Hadley named it melt. And so that's the mnemonic for why things are the way they are named. There are a lot of weird puns going on in the R world and how they name things, so this is just what happened. So we'll be using the same melt function, right? But this time it's a little bit different because we have a bunch of other columns that we want to hold still, right? Before it was just religion. Now we actually don't want to touch the year, artist, track, time, date entered. I think that's it, right? Yeah, it goes from 1 to 76. So the first 5 columns we don't want to touch. And so this is when we have ID vars and we specify those first 5 columns. So it's year, I have it written because it's so zoomed in I can't see. So it's year, artist, track, time, and date dot entered. And if we want, just like before, we have the value name. So when we take those week numbers, when we sort of melt those down, the actual ranking, instead of value, we want it to be called rank. And then the actual week, those column names, we actually want that to be called a variable called week. Right? All right, so now this is a data set that I would say is a lot more suitable for doing some kind of analysis. So like we can say like, hey, for a given week, what was its actual rank, right? So what do I mean by that? So think about like what we did in our first notebook was we ran a bunch of group by statements, right? So we can then say, hey, let's group by for each artist, pull out the rank, and then give me the mean, right? So this gives you what is the average rank for each artist in our data set. It's not going to be sorted. There's ways we can sort our data set, but this is something that we couldn't do in the original shape of our data set before. You'll end up having code that sort of looks like this. What you'll see a lot in the pandas world is putting a break between anything with a dot in front of it, and then wrapping the whole expression in a set of round brackets. Right? So to make your code look a little bit more like the pipeline, this is how a lot of the people in the pandas world write their code. So you can say like, you can even do something like this. If you are super into that piping syntax in the R world. So given a billboard data frame, we're melting it, we're grouping by something, and then taking a mean, right? So you can just look down a column and get a general sense of what's going on. And so the other way you can do this, I'll just copy and paste it and show you. If you didn't know, like I did, that you can use round brackets, you'll see this backtick. Sorry, not a backtick, this backslash. And this is how Python reads in like, hey, the next line of code is really a continuation of this line of code. So either way works. I sort of used to write things this way, and then I realized, wait, the round bracket thing actually looks a lot nicer. And so that's really your own preference. But this saves you from having this like 300 character wide bit of code. If you're trying to keep with like some kind of PEP 8 standard of like limiting things around to like 70, 79 characters, like this is what you would do. Right? Yeah, so the question was like, hey, if some column got read in as like, for example, a float when you wanted as an int or something. Yeah, I'm not going to cover it, but pretty much there is a method called as type, and you can coerce a column into some other type. If you're trying to coerce a column into a numeric column, so you can say like as type, like object or string, right? Or character. Actually, no, not character, but like object or string. But if you're trying to coerce things into a number, instead of as type, there's one called to_numeric. I think that's what it's called. And what that does is sometimes you'll end up with a column that you expect to be numeric, but because like someone put in like, for example, like NA, the string, the column can't be read in as a number anymore. And so if you use to_numeric, there's a feature, there's a parameter in there that says like coerce everything into a numeric value. And so when it can't coerce a value into a number, it'll return a pandas missing value versus, because otherwise it'll just be like, I can't deal with NA, the string. I don't know what to do with it. So that's like the quick and dirty way to be like, hey, this is supposed to be a number. I don't care what other bad values in there. Just convert it into a number. And if it can't, just report back a missing value. All right. So any questions about that? So that was like the first problem. What happens when you have columns that should be individual values in rows? Just use melt. All right. So the next part in this paper, we talk about multiple variables stored in one column. And so I have so my master's is in public health and epidemiology, and we get a lot of data sets from like the CDC, or when I used to work with CDC data. And so they have this, a lot of their data sets come from, actually I'll show you in this paper. We're not going to be using this example, but a lot of CDC data come in formats something like this, where you can see for a given column, we have M014, which stands for male 0 to 14. And there's the equivalent one for like female 014, et cetera, et cetera. Right, so for a given column, there's 2 bits of information encoded, right? So if this was a count, we have 149 males between the age of 35 and 44. That is not useful from a data analyst perspective, because what if you wanted to fit a model where male or gender was a variable? Like, you need to separate out gender and age group. All right, so PD read CSV. So there is this data set that one of the doctoral students, when I first started my PhD program, Caitlin Rivers was a PhD student during the 2014 Ebola outbreak in West Africa. And what she ended up doing was like took in the PDFs from like the Ministry of Health and sort of documented their reported case and death counts and created this data set for us to use. And so again, the way you input data, as long as you know or you have some way to transform it back into a tidy data set, like just think about like how you're going to set up your data input process, you can have a case where it's set up this way, cases, Guinea, and account, because that's how the Ministry of Health were reporting things. So it just became convenient to store your data this way. But we have the same problem here for a given date of the outbreak, and since the first day of the outbreak. So for the first day would be, the first case was March 22nd, 2014. We have whether or not this was a case count, or on the side we have whether or not this was a death count, and then for a particular country, right? And so for each column, we have this problem of, hey, how do we know this is a case count and a death count? And then what country is this thing counting? And so how do we fix this problem? Well, when you have this situation, you kind of have to do 2 steps. The first step is just like before, we need this thing in long format, right? And so I showed you how to do this, convert into long format already. We use the melt method or melt function. So let's first do that. So the columns or the ID vars that we want to keep consistent is the date column and the day column. And then the variable name, so when we sort of melt this down, what is their new column going to be? I'm going to call a CD underscore country for, is this a case count or a death count underscore country? And then the value name I'll call count. And let me put a new line here. All right. So if we melt our data, we're almost there. At least it looks like we have a column called count, so that's good. And the next thing that we need to do is how do we break up this column into whether or not this is a case count or a country. And you'll notice that, hey, one simple heuristic to do this is if we split this up by the underscore, we can get the thing to the left of the underscore is a case death count, and the thing to the right of the underscore is the country. So how would we do this? So if we backtrack a little bit into strings in Python, this is using the string methods that are already built into Python. So I think if we Google, like, this usually almost never works. I always end up on like the Python 2 documentation for this. But there is all Python strings have this method called split. And they can do a whole bunch of other stuff too. So what does that look like? So we have something like this string called, like, I don't know, right? So that's my name. If we say dot split, and we want to split by the, whoops. Well, if we split by something that doesn't exist, it doesn't exist. But if we split by like the underscore, you'll see we get a list back. The delimiter gets removed, and then each individual piece we get back as a list, right? So we can do the same thing. We can take this same idea and apply it to our data frame. And so the way we do that is if we, oh gosh, given our Ebola data set, we're looking at the CD underscore country column, right? So we pulled out that column. So how do we do this split notation or this split thing on our column? The way we do that, so I already showed you LOC, ILOC as like accessors, or like ways of accessing different things that you can do with a column. The next one I'm showing you guys is str. So now you can treat like this column as a string, and you have access to pretty much all of the string methods without having to write a for loop. So str split, and we will split by our underscore. And you'll see that now instead of, we get the same results that we got back originally, which was, hey, it's split by an underscore, not a dash. I put a dash. All right, there we go. So if we split by the underscore, we get the results that we got before, which the delimiter goes away, we get a list back, and then every part that got split becomes an element in that list. Cool. So if we go back to, yeah, so let's save this var split. All right. So let's look at what's going on in here. So if we type, we'll see that var split is a series, right? So it's just one column. That's what's actually being represented. For this series, if, for example, we wanted to look at the first thing, so that first object in that list, this is really the same thing as looking at .iloc, is a regular list, right? So Python lists, if you've worked with Python before, like treat this, pretend I didn't type any of that other stuff. How do you subset things out of a list? You use square brackets, right? So for example, here, if I wanted to get my first name, I would put in square bracket 0 to get my first name back. So we can do something very similar here, treat this as a list, and then say, give me the first element, and it'll give us that first element back, right? So we need to replicate this behavior across that entire series. And so the way we do that, so we have this split column. How do we sort of essentially do this subset 0? You'll see people just write subset, sorry, dot str, and then subset 0. People do things like that. I prefer to be a little bit more verbose and just say, like, I'm trying to get the first element. And so I write things like this. And so that's great. We have an entire column of whether or not this is a case count or a def count, right? So we can say this is a, what did I call this in my notes? I call this status. And then we can do the same thing for the other column, which is, I think it was just country. And we can get the second element, right? So now if you look at status, we get all of the, whether or not this is a case or a def count. And if we look at country, this is a column for the country. And just like before, how do we clean this up? We can put this back into our Ebola long data set. And we can say status is equal to this status column that we just created. Ebola long. Country is going to equal that country column that we just created. So now if we look at our Ebola data set, that's how you take that column and parse it out, right? So this is, at least for me, like most of the type of work that I end up doing when I'm cleaning data is like, yes, most of the time it's not going to be as simple as like parsing by a delimiter. It's going to be some weird regular expression thing that you're going to have to write. But if you end up with a data set that has column or multiple things stored in one variable, like this is roughly the steps you're going to have to do. You're going to melt it, and then you're going to end up processing somehow those columns that you created. There is a shortcut for, or somewhat shortcut for this. So if we go back to split, I think right now if you, yeah. So why did I show you those string accessor or the documentation earlier? It's because split can actually do a bunch of other stuff that if you do like shift tab right now, the documentation won't show up. So how do you actually go find that stuff? So you would look up Pandas series, go to the series documentation, and I think it's under accessors. Yeah, so under accessor, under string. All right. So series.string, so we just had a column name .str. We looked at .split. So you'll notice that a lot of these methods are actually the same as the built-in Python methods. If we look at split, that's how you get to the actual documentation for like figuring out what else split can do. And I bring this up because there's this parameter called expand. And so instead of giving you back a series of list objects, it will just give you back a data frame, which is, if you work in data frame world, that's what makes you happy. So if we say expand equals true, you'll see that we get a data frame back. It's not named properly. It just says 0 and 1, which is fine. But what you can do is Ebola long. If you have a data frame like that, case 2, country 2. If you have a data frame and you want to sort of add it to another data frame, oops, I don't know why I keep doing that. Essentially concatenating or appending. Just pretend that those columns exist. You just have to, because you're specifying multiple columns, know that you have a list inside. And that's sort of like the other quick way that you can just tack on values to the end of another data frame. All right. Cool. All right, so the next problem, yeah.
Is it normal practice to like then delete the old column, or would you just leave it for like?
It depends on where it's going to end up and how much space you have on the computer that you're working in. I usually try to keep track of all of my columns, and then at the very end, when I'm like, oh, this is what you need for someone else, like I'll drop things along the way, or I'll also reorder things so they actually make sense. Because I've done like papers where, like, for example, something as simple as like, here's the column of means, and I write this whole function that calculates the mean given a whole bunch of other things, and then I realize I actually need the numerator and denominator as separate things. And so it's just sometimes way easier just to have your work in your data frame. It also helps like spot checking if you've missed anything. Because sometimes if you calculate the mean and one of the values missing, you just have a missing value, and you're like, okay, why is this thing missing? You're gonna have to end up backtracking and doing it anyway. So if memory or resources permit, like I just try to keep things. Like in this case, I would have just called it status and country instead of case 2 country 2. That's just to show you guys. But yeah, I usually try to keep as many things like so I can quickly spot check what's going on. All right, the last piece of this paper. Where is it? All right, so I showed you what happens when column headers are values, not variable names. We showed you multiple values stored in one column. Now you have the problem of like, what if like things are like really weird and you have rows and columns, data stored in rows and columns like both ways. And so we have a data set for that. It is the weather data set. All right. So if we look at this data set, you'll notice that the melting operation is going to have to be done because we have like a bunch of days and like values for them. But how do you know you have this other problem of like, hey, this element column is temperature min and temperature max. So if I were to take out my piece of paper and describe like what is the data frame that I actually want, I would really want a column of ID, year, month, and day, and then a separate column for the min temperature and max temperature. Right? So in this case, this element column is storing values that really should have been columns and not as individual rows. So we actually have to undo the melt step. A symptom of you knowing whether or not you need to undo a melt step is pretty much if you look across a row and a bunch of values are repeated except for like one, that's a pretty good sign of like, hey, something's wrong with one of these columns, right? So if you have a bunch of repeats, that's a good sign of some of this values being stored in both rows and columns. So the way we fix this is, well, we first deal with the melting aspect first. So we take our weather data frame, we melt it. The ID vars. So these, again, are the columns that we don't want to touch. So it's ID, year, month, element. Right? So that's the melting part that we've been working with this entire time. So the next thing is we want to pretty much undo the melt for this element column. How do we do that? So let's save this to weather long. So the way we undo melt is this function called pivot table. All right. So if you've worked in like Excel and you've done pivot tables before, there's something that's nuanced that you need to be very mindful of. And that's why there's two versions of this pivot function. There's pivot and pivot table. You can imagine that our weather data set, if you had multiple people taking readings for a given year, month, day, and temperature min, you would have multiple readings, right? So in our longer data set, we would have a problem in that we would have a problem in that, like, for example, we would have two values of temperature max for a given day, right? Like, we'll have duplicates. What was your question? Oh, yeah. So the question is like, was the question, what's the difference? Oh, so they're both the same thing. So you can say weather.melt or PD. Oh, I would say that is so if weather.melt isn't working, I believe that is a pandas version difference. Yeah, so they sort of there was a whole bunch of one of the versions was like, hey, there's a whole bunch of weird inconsistent things going on. Let's just make it consistent, and that would be one reason why. Yeah. But yeah, pd.melt does exactly the same thing. So, okay, back to this. If we do have multiple values or duplicate rows, you can imagine when we sort of make this data wide or pivot this table, what does it do with that duplicate value? Like, you have two values. What do I do with this thing? Because a cell can only have one value. And so that is the difference between pivot and pivot table. Pivot just assumes that you only have, you're just doing this pivot, and if there are duplicate values, it will cause an error. Pivot table, there's a lot more parameters involved, and one of those parameters is this ag function. So what do you do with multiple values? By default, it takes the numpy mean. It takes the average of those two values, right? So I think this data set doesn't have values, but I don't want to do too much random live coding that I don't expect. So, but yeah, so in general, that's something you want to think to yourself, like, what do you do with multiple or duplicate values? You might want to check to see if there are duplicate values to begin with. But for the most part, if I get duplicate values, like the mean is pretty good. You can also say numpy.min or max or any other function that returns one value back, right? So it's ag function, just like the group by aggregate, takes in a bunch of values, returns one back. So pivot table is the function that we'll be using. The parameters for pivot table are similar. So you can imagine that we're going to take this element table and spread it out or pivot it out. So what's going to happen is for each unique value of element, so in this case it's tmin and tmax, those become separate columns. So we have a separate column called tmin and tmax. And then we also need to specify when those new columns get created, what are the values in those new cells? So we also have to specify another column that's used to fill in those values. So let me show you what that looks like, and then hopefully that will make a little bit more sense. So the parameters are similarly named. So we have our index, which is like our ID var. So these are the columns that we want to keep consistent or not move. Yeah, I should have called that day, but that's fine. So these are the columns that we don't want to move. The next parameter is columns. So here, this is where you specify the columns that you want to pivot out. So we want to move the element column, and then when we pivot out the element column, what is the column that we want to use to fill in those values, right? So, yep. So we end up with this data frame, which looks funny, and this is, again, in a multi-index. But this is what we get. We have our ID, year, month, and variable or day, and then a given temperature, max, and min. All right, cool. And then, like I said, if you end up in this weird case where you're dealing with a multi-index and you just want to flatten everything down so you get a regular data frame, you can say dot reset index, and you'll have your data frame that you are used to working with. So now you can actually fit a model something along the lines of like, hey, for a given month of the year, what is the min or max temperature? Or you know, how does min and max change like across a given year or something? All right, so one last small thing before we move on to the next topic. This is just something that's sort of cool in Python that I recently learned that I didn't know about, but it's super useful. So we have like numbers in Python, and something that's super useful. The reason why we have like comma as like a thousands delimiter is because like it helps us separate like how big this number is. So you can do that same thing in Python, just use an underscore, and it's treated as the same number, right? Yeah, super useful. So you're not like, how many times did I click the right button? So I found that super useful. This is just built into Python. Super useful. Another thing that's super useful that like, so I also work in R a lot, and this is one of the things I've noticed as like one of those quirks in Python that's super useful. So for example, if we had like, you know, sometimes if you have a bunch of lists and you're testing something out, you know, it's kind of useful to have each element in the list as its own separate line. What is useful about Python is lists can end in a comma. And the benefit of that is if you have a bunch of parameters and you're trying to comment out the last one, you don't need to comment out the last comma, right? That's super useful, especially if you're doing like version control stuff, where like you're really just changing one line, but like every time you do this, like it's two lines that get changed. And so what that looks like is like we have 1, 2, comma 3, right? So I can comment out this last number and it'll still give me the same. It won't give me an error. Versus like if you've ever like had to do that and you think you have to do that, like you actually don't have to do that. So that's something I wish R did. but there are also a bunch of things that like I wish it works both ways. But all right, so we'll take another 10-minute break. So come back. Hopefully there's still snacks. What time does this thing end? 12:20, right? Okay. All right, cool. We'll there's only one topic left, which is yeah, we'll come back. And then I'll put down a small exercise for you guys to work with during. So it's 10 minutes. So come back at like 11:20. All right. Yeah. Don't just disappear. Yeah. This one? 49. 49 disappeared. This one? This one. Yeah. 2 columns. The trick is this data frame has 2 columns, and I want it in, instead of assigning one column at a time, you can just do it all together. So this is just like a quick like way of doing a bunch of things in one step. Yeah. Yeah, because otherwise you have to pull out one and rename it separately. It just saves you a little bit of time. Yeah.
Right in the middle of the thing, my notebook failed.
Oh, that's not
I
good.
had to reinstall. I had to install my virtual environment, new virtual environment.
Uh-huh.
So I lost track of a few things.
Okay.
So yeah, one question is that when you did the last melt,
Mhm.
you use values equal value.
Oh, yeah, yeah, yeah.
You may have explained that earlier, but I missed that.
So this part, yeah.
Yeah.
So this is part of it. This is my fault because so if you come back here, the column names is variable and value. Is referring to this column name.
Is it something that it did by default? Because yeah.
It did it by default. Like what I
Okay.
should have done here was actually like name these, like var name is day. Value name is
Okay, so what
temp.
your name now day used to be okay,
Yeah.
variable now.
So then it would have been temp right
Okay,
here.
and then you would update that to valuable temp. So
Yeah, and this would have
because
been
you knew
day.
the default things, so you
Yeah.
put that. Okay.
Yeah. So that line value equals value. Yeah, I realized like
That's fine.
I just forgot to do that, and and yeah, that's super confusing. But
So
that's
is
why.
this, so that I can actually catch up later. This Python notebook,
Mhm.
is it the one already online in your GitHub page?
Yeah, it's pretty much the same one.
Yeah,
Yeah, you
it's
can copy and
ID1,
paste it.
okay.
Yeah, there's gonna be a block that like I sort of just skip over, but I'll just talk about it, which is the last bit of tidy data. But
Yeah.
that has more to do with data engineering, not data cleaning.
Yeah. Okay, no, that's good.
But yeah, so you can copy paste. Let me just show you. It's number. Yeah, it's like whatever 30 is.
Okay.
So this is what's on the GitHub page right now. So it's like
Yeah.
variables stored in both rows and columns. And so
good.
if you just copy that down, that's
Excellent.
exactly what I'm using to teach you guys. Yeah. Oh yeah, it's a lot. Yeah. The good thing is this stuff is recorded. I think I've heard somewhere that like the recordings are, you might be able to correct me, but like the recordings are like up within like 24 or 48 hours, something like insane. Like definitely socialize with other people, not just like go home and watch everything else that you missed in a day. But like, say again. I think they're on YouTube, so they're just like forever until Google disappears, you know.
Until we get hit by that solar flare that just ends all this computer stuff once and for all. Stop that now.
So of the people who are here right now that are somewhat paying attention, who's like never I'm assuming you're here because you never worked on like the data frame side of things, but like how many people are totally new to Python as a language? All right, cool. Yeah.
So this Panda concept is more of like normalizing data table in database in a different syntax. Because you get lots of data, data of MySQL, there are 5 level of normalization. So I believe this one,
Yeah. Yeah, so normalization is like a very specific term. Um, I'm going to show it to you, just explain it. Yeah, databases take normalized tables. So like usually when you're processing and analyzing data, you undo all of the normalization in a database because joining a table means you're unnormalizing the data set. So yeah, so pandas is just like how do you combine a bunch of tables together so you can do an analysis, if that makes sense. I don't know. Yeah, you said normalization. I was like, wait, that's a very specific word.
it was like more of like the concept of dealing with data in database, normalizing table, storing. But here it's like similar concept, but
It's the yeah. Yeah, so it's like this is what you do to get data out of tables or databases, or this is the cleaning that you do before you put it into a database. Yeah. All right. Okay, so I fixed the clock on this machine. It is currently in the right time zone. Yeah, so I gave like one of these tutorials once at like PyData Research Triangle, like the Carolinas area, and like I did a last minute swap with someone, and I didn't realize that like the tutorial swap time was like it wasn't that the computer's time was off, but like my tutorial slot was just 45 minutes shorter. So that was a whole like, oh, I guess it's over now. So, all right. So the last thing that the tidy data paper, which you don't need to read the whole thing because the very end of it actually just goes through a case study in R, which you don't need to read. But I'm not going to go over line by line of what's going on, but there's this idea of data normalization, which is that last couple of points in that tidy data paper of like what is an observational unit. So if we think about the Billboard data set, you'll notice that for the year artist track time date entered, all of that information is repeated, and that is like the symptom of like, hey, before you start dumping these tables into a database, or if you're like a database engineer, this is something you care about because that's a lot of repeated data, and if you think about like billions of rows, that's a lot of space. So how do you, you don't do normalization when you're like trying to analyze data. Typically when you're analyzing data, you're just combining everything together. You're pretty much undoing all the work database people do. But that's the whole point, is to be able to combine data sets. So to undo it, you'll see that like, for example, I'm assuming, I expected this to be like a Beck song, not Three Doors Down song. But you'll see that like for loser, the track, like a bunch of information is repeated. The only thing that's not repeated is like the week number and the rank, right? So like there should be a way that we can capture all this repeated information and represent it by like one value, right? There's no need for all this replication. So the way you would do this, there's a bunch of steps, but there aren't really that many new real concepts. So the first thing you do is like take those columns that are having those heavy repeats, you'll subset it down. So this is doing that double bracket notation to subset multiple columns. So we just have our year artist track time. Here you'll notice that this has about 24,000. Oh yeah, whoops, sorry, yes. All right, so here you'll notice that there's 24,000. Yeah, this is way better. I figure like if I'm squinting, like that's really bad for you guys. So 24,000 rows in this data set. So there's this function or this method called drop duplicates. So you'll notice that if we drop our duplicates, we end up with 317. So that, like there's really only 317 songs in our data set. But because it's week 1 to 76, like that's why there's so many repeated values. So the other trick when you're trying to do normalization, I bring this up because like part of my previous job was like as a data engineer, so like it was my job putting stuff into databases, and this is what you had to do. You have to, when you normalize data, the end goal for the user, like for you guys, when you want to analyze it, is you want to put data back together. So you have to be really careful that like, or be really mindful that when you, the analysts, when they put data back together, that there's some kind of key to join things back together, right? Yeah.
Yeah, the drop data, that's comparing the ID view. Well, what is that comparing against?
Oh, the drop duplicates?
Yeah, drop.
So it's pretty much going like for each row, if a second row has like identical values for each of the columns, it just drops it.
Okay, so it's comparing each column that you put in, or?
Yeah, yeah. It's comparing each column.
I see.
So here I just say, hey, take the that row number on the side and just create that as an index. So for a given year, artist, track, time, it gets represented by something. So here it's just a number from 0 to 4. So if you're working with database a lot, like that's like auto increment. It's just like it's an ID or an integer value. So the next thing, I didn't really cover it. If we had like another hour and a half, we'll go over joining and merging tables, but you can combine tables in Pandas as well. It's very SQL-like, SQL-like. So we can merge these tables together because the problem now is we have this ID column, which is our key, and if we wanted another data set of like week and rank, we needed the key in that data set as well. So we needed to join those tables back together just so we have this ID rank again. And then the last thing that you do is you take essentially the week rank columns that you care about. You make another data set that just filters on like this. In this example, I kept date entered for some weird reason. That's the information that you care about, and so you filter that out. So you end up with a data set that is ID, essentially week and rank, and then those are the values that you write to a database or you write to a CSV and you give it to someone else. First thing that they'll probably do is just undo all of that work and join it together. But what that means is your data sets that you're sending across the internet is smaller. The one thing that you want to do is when you're using to CSV, typically this index right here, for the most part, for most cases, doesn't mean anything. And so you want to set index equals to false, because otherwise it will write a columnless, a column with no name that's just the index value. And when you load it back in to Pandas, it's going to be like, oh, I found this random column that doesn't have a name, and now you have like this extra column that doesn't mean anything. So you want to set index equals to false if you're not actually using the index for anything. But that's it. All right. So we will do this last bit, and we will marathon the last bit. Writing functions in Python. So what we've been working with functions, they're like methods. So there's like this technical definition of a method and a function. A method is usually like DataFrame dot melt, right? When you say dot function thing, that is technically a method, versus like arbitrary functions that we were calling. So like pandas dot read CSV was this other thing that wasn't connected to any real object. So that is a function. So the other way you can think about it is like a method is like objects can do things, and those things objects can do are called methods. And then other things that you just create are functions. So the way we create functions in Python is this def keyword. So def, a lot of times it will turn into some other color, followed by the function name, a set of round brackets. So this is a function that doesn't take any parameters, but if you had additional parameters, you would give them names in here. A colon, and then everything after the colon needs to be indented, like 4 spaces or 1 tab, and that is the body of the function. Here, if you have, I have pass because if you just have something empty, it like actually doesn't like that. So if you want an empty function, you have to put in something. So a really simple function then is like, let's write a function that like for a given value, we square it. So functions need to return something. So I jump back and forth between Python and R like all the time. And like yesterday when I was rewriting all of this stuff, yeah, in R is a freaky language sometimes because what happens in R is the last thing in a function just gets returned. Like you don't have to have an explicit return statement. But yeah, so in Python, if you actually want this function to return something, you need the return statement. So we're saying x star star 2 for x to the 2nd power. And the way we use this function, just like our pandas read CSV, we can say my square, and if we put in 4, it'll give us 16. One thing you really want to do, just to get in the habit of, is typically when you write a function, you're going to do something like this just to make sure your function makes sense, or it like did the thing correctly. And some of the tutorials or some of the talks, they'll talk about like testing in Python, and just get in the habit of like testing. And the easiest way, especially when you're like in data science, the way you actually end up writing tests in Python is you use this assert statement. So just get in the habit of writing them. So this is a test statement of like, hey, does my function that I wrote equal 16? Because that's what I expect. If it's false, it'll give you an error. If it is true, it'll just silently go by. And think about this when you're working with data as well. If you're working with sensor data, a lot of the times, like sensor data comes in very, very specific shapes, right? Like a shape as in like your readings from this sensor has 300 rows and 300 columns. Like read in that data set, and you can write an assert statement that says like assert dataframe.shape is equal to 300 column 300, comma 300, right? Because that way you can immediately just have your script fail if like you just had a bad sensor reading for whatever reason. So, and that's all you need is this one little keyword, assert. It'll save you a lot of headache if something were to go wrong. All right. So if we wanted multiple parameters, instead of, like, for example, x, we can say x comma y. And we can say, how do we calculate the average of something? It's those two values divided by 2. And then we can say, actually, I'm not going to say my average, because I think my notes here are like somewhat specific in terms of how I name things, so I don't want to mess that up. Right? Average 2. Right? So if you have multiple parameters, it is in the parentheses or the function signature, you put a comma, and then those are the variables that you'll be using. So that's writing functions in Python. So how do we apply them to data frame objects? One thing that you'll hear somewhat often is like, typically when you're working on a data frame, you don't need to write a for loop. Because like I said, like a lot of things just happen automatically. They just get done on a row by row or column by column basis. So you just want to get in the habit of like using what's already there. One thing you definitely don't want to do, which I believe applies to Python as well, is like you don't want to like append to a data frame in a loop, right? You don't want to create like a change in a data frame in a loop. That's like usually really bad. So let's create a data frame. This one will be super simple, just to show the point. So we saw this before, so we're going to have 2 columns. A, it's going to be 10, 20, 30, and then we will have another column, 20, 30, 40. And I did not import pandas. Import pandas as PD. All right, cool. All right. And so we have this example data frame just to see how applying works, because there's a few things about apply that are like a little bit tricky. So I showed you already, we can take like for a given column, we can perform these mathematical operations, and it'll just work in a vectorized fashion, right? We don't have to loop over every value of A. We can just make these calculations, and it understands that like, hey, we're doing this on a row by row or element by element basis. All right, so how does that work? So we're working with one column, right? So let's first see what happens. How do we take our function that we wrote before, which was my square, and how do we square each value element-wise? The way we do that is we call this apply. Oops. How far do you want me to scroll up? Like this part? Okay, cool. Let me do that. All right. So we use this apply method. And so if we hit Shift Tab and look at what's going on, apply, the first element in apply is it takes a function, and then it takes an axis, right? And if we look down here, an axis, do you want this function to work row by row or column by column? Sorry. If we go down here, 0 for index, which is apply to each column, or 1 or columns to apply to each row. So by default, it will work on a column by column basis. You could change it to a row by row basis, but in this case, we're working with one column, so there's no notion of columns or rows. It's just one thing. So here in apply, we just say what is the function we want to apply or put in, and we can say my square. So that's the function we just wrote before. And what that does is, like, for every element in this column, it got passed into the function we just wrote, and then gave a number, and then when it's done with all of it, gave us back one series back, right? So we did not have to write a for loop, which is the key thing to understand and see. Yeah. Yeah, not writing for loops is super cool. And then like you work in base Python, and then you realize, oh yeah, map and reduce are like built-in functions too, and you just stop writing for loops. Yeah. It is not multi-threaded. It is not multi-threaded. There are libraries, I think, that like do it for you. I might be conflating this with R now that I think about it, but yes, like it is an embarrassingly parallel thing that you can make parallel, and I'm pretty sure there are libraries that do it for you. But yeah, by default, it doesn't set up the forking and thing for you now. All right. So what about functions that take multiple parameters? So let's say like we write a function that takes in a value and returns it and raises it to an arbitrary exponent, right? So we can do something like 4 squared, or maybe we wanted like 4 cubed, right? So now we're saying like, hey, this function takes one argument that relies on some value in our data set, but the other argument is something that we can just manually set, right? It's not data dependent, and so that's the key distinction I'm trying to make right now. And so if that's the case, we can pretty much do the same thing just like before. We can say we're applying the myexp function, and if we want to pass in a value for the other parameters, we just pretend they exist as keyword arguments. So e equals, let's say, 4. And then, without writing a for loop, we'll go raise each one of those elements to the 4th power, right? And we get a new column back. Again, also know that this returns back a series. So if this is a calculation that you wanted, you could have very easily been like A4 equals, and you could reassign it back to your data frame. I'm not going to do that because I actually need this data frame for like teaching purposes, so I don't want to like mess it up too much. All right. So that's with a series, right? So series are pretty simple because it's only like one dimension of data. But if we think about data frames, they have at least 2 dimensions. that we have to deal with. So that's why the index or axis comes into play. Do you want this thing to work row-wise or column-wise? And just to show the point, we're going to write a function. It doesn't do anything other than print exactly what you give it. And this is really just to show you what happens when you apply functions into a data frame. So we have our original data frame. Data frames also have this apply method. And it works exactly the same, or it looks exactly the same as the series. We give it a function, and then we tell it what axis to work on. So the function that we want is print me. All right. So the part I have selected is what got input into the function, and then at the bottom is what got returned. So this function doesn't return anything. That's why we get none, none. We get two nuns because by default, when you apply on a data frame, it operates on a column by column basis. So we only have two columns in our data frame, so we got two values back. What I have here is, here's the actual point that's important, is when you apply on a data frame, or in this case, when you apply on a data frame that goes column by column, that entire column gets passed in as the first argument of that function, right? So everything in that column, or if you have the other axis, everything in that row gets passed in as the first argument of that function. So that has some effects as well. So if we define another function, like average 3, that takes in x, y, and z. So it takes in 3 parameters. Right? We have a function that takes 3 values. And if we try to do something like df.apply average avg3, each column has 3 values. And if you try to apply, it's going to say at the very end, hey, like, I'm missing 2 things, y and z. It's because, again, the entire column got passed into x, right? It doesn't know to break up your column or those values. It doesn't know to separate that out. So there's a few ways that you can get around this. It's not really a limitation, but there's a few ways you can get around this. If you're doing numerical computation, you'll probably be importing Numpy. And 3, apply, right? Right, so Numpy understands, like, hey, if you pass in a whole entire vector of values, like, I can calculate the mean on something like that. Right, so if you're doing numerical calculations, you're probably importing Numpy just because it understands, like, how to deal with arrays and matrices. So if we say something df.apply average 3 apply, like, this now all works because when the entire A column got passed into our function, Numpy mean understands how to deal with, like, essentially an array of 3 elements. If you wanted to do this yourself, knowing that everything got passed into the first argument, you would have to take you would have to rewrite your function so that everything that entire column or row gets passed into one argument. So you'll just assume, like, hey, maybe the entire column gets passed in. And then internally, you'll have to sort of, if you already worked out the calculation, you would have to break it up internally. Right? So you could, if you already knew, like, hey, this is the proper way of calculating the mean of 3 values, you would have to do some rewriting such that your function takes in everything in one go and then break it apart internally and then make the calculation that you did before that way. Yeah. So because this function takes in 3 things, let me show you what happens when you change the axis. So by default, axis is 0, and if we look at our documentation here, 0 or index goes column-wise. So we can say 1 or column. So we can say axis equals columns. So this is also something that's new in Pandas or in the newer version of Pandas. It used to be you can only specify 0 and 1. I am very happy that they allow you to put in rows and columns. But you'll see that the problem here is now we said, is this right? Did I put in, yeah, that is right. So this is now operating on a row by row basis. Sorry, too much. Row by row basis. So our data frame for each row and has 2 values. So when we ran our function and it's erroring because like we're trying to do a subset that's out of bounds, right? So that's something to keep in mind when you end up doing something like that. Right. So I gave you the example of like, hey, we're just doing these simple calculations. Like we could have very easily have just done something like df a dot mean or df a plus df b. Like we could have already done stuff like this. Why? What's the point of like showing you this example? Well, let's say for example we define another function that takes 2 values x, y, and if like one of these values is 20, we just return np.nan. So nan is how this is how you get a missing value in Pandas. It's missing values in Pandas come from NumPy. So if you ever need to just work with a missing value, you pretty much have to import NumPy to use it. There's 3 ways you can use nan and with the n's capitalized, or all of it capitalized, or all of it lowercase. They all are exactly the same thing. I use capital N with the n's capitalized because that's how it shows up in your data frame with the n's capitalized. So it doesn't matter in that sense. So let's write this other conditional. If the first value is 20, just return a missing value. Let's say that's just a bad value. In like a lot of medical or health data, like 99 or 88 get encoded as like, this is someone explicitly putting in a missing value so you don't get confused, like, did the analyst just forget something? Otherwise, let's do the actual calculation, right? So this is a function that actually is different, right? So if we have our average to df, so we could have easily have done this as well because, again, there's broadcasting going on. We didn't actually have to run apply to do this stuff. If we wanted to do it element-wise, so pass in all the values of A, pass in all the values of B, calculate the element-wise average. We could have done that this entire time. But let's say, for example, we now want to use this version of this modified version. This no longer works, right? So we actually have to do something different here. So let me show you df a, df b, right? And the value error, it's really just because like I don't know how to deal with. It's pretty much saying if a series returns back true, false, is the series true or false? I don't know, right? So that's the actual error that it's giving. But we really just want this to work element-wise, right? And instead of like having, I showed you could deconstruct this and rebuild it such that it passes everything in as the first argument of the function. But there's an easier way to do this. And it has to do with vectorized functions. All right. So the way we do this is we import NumPy. So if you ever wrote a function from scratch and you're like, hey, I want this to work on these 2 columns in my data frame element-wise, and I don't want to rewrite everything, there's a really quick way to do this. So in NumPy, there's a function called vectorize. And vectorize is a special function because in the sense that the input to this function is really just another function. So instead of like a number or a string or what you typically think that you put in as inputs to functions, this is a function where its input is another function and it returns like some augmented version of the function that you put in. And so the version of the function that we're going to put in is average to mod, right? Because this is a function, if we put in a and b, it didn't know how to handle like this truth value thing, because all of the entire column got passed in as the first argument. It did work if we just passed in each argument individually, right? So if we pass in our original function to the numpy vectorized function, we can see that all we get is this memory mapping, which is really pointing to another function. So let's save this. Right, so it's really the same name. I'll just underscore it at put vec underneath. So now if we run this, df a and df b, it understands. It actually understood that we wanted everything to be put in one element or like element wise instead of just dumping everything into the first argument, right? So this is essentially like writing the for loop for you. It's iterating through each row, for each row taking the corresponding piece and putting it into your function, right? So you don't need to write the for loop if this is what you're trying to do. So this notation of a function that takes another function as its input and returns like some augmented version of that function is common enough in Python that there's a shorthand or shortcut for this. So let's go back to our original function definition. Actually, I'll just rewrite it because I'm not going to be able to find it. It's way too zoomed in. All right, so let's say you're writing your function average to mod. This is taking x and y. If x is equal to 20, return numpy missing. Otherwise, return the actual average between the two numbers, right? So I already wrote this function. And I know I'm just going to end up passing into numpy vectorize and get a vectorized version of this function. So again, this notation is so common. This is what a decorator is. A decorator is how you decorate or mark the function that you wrote, and what you pass in after this @ sign. So the way you specify a decorator is right before you write your function definition, you see this @ and then that is the function that wraps around the function you just wrote. So this line right up here is exactly the same thing as saying @numpy.vectorize. Right. So what I did up here is exactly the same thing as what happened down here. Except now I don't have to create this, I don't have to assign it to another function. I can just use this function as if nothing has changed, right? So it will automatically vectorize this function for you. And so now if I run this, I can do exactly the same thing as I did before, pass in df a, pass in df b, and I get a vectorized function pretty much for free, right? So I don't need to reconstruct the signature of my function. So this is useful because you can write your function, write your test, do whatever, just wrap the whole thing in vectorize, and then now you don't have to write the for loop in your actual data frame. All right. So if what you're doing in here is purely like mathematical or numerical calculations, there is, oh boy, I really hope this came with Anaconda. All right. There's this library called Numba, which pretty much just takes a bunch of things in NumPy and makes them faster. It's just my understanding of it. I don't do that much like math work or calculations, but if that's like the work that you're trying to do, Numba is a library to look into if you're trying to make your matrix calculations like just faster. So we can do the same thing. Numba has a decorator as well. So instead of numpy vectorize, it's called numba vectorize. So I'll copy and paste the thing from before. I will rename it so it's numba at the end. But just like numpy vectorize, it's numba dot vectorize. Cool. Numda. All right, cool. All right, so we now have like this vectorized form of this data frame. So now the problem is Numba doesn't understand what a series is, right? So like I said, like certain libraries, when you leave pandas, like make really strong assumptions of like, hey, we're only speeding up NumPy calculations, so we should really only expect NumPy arrays, so we can just make that assumption and make our code faster. So like I said, like in the very beginning, how do we oh yeah, how do we get the actual NumPy representation of all this stuff? We say dot values, right? And then when you start leaving the pandas ecosystem, this is some of the things that you'll have to do. One cool thing about the Jupyter Notebook is that there are these things called magics. One of the magics that are super useful is you can time, so you can use, I think it's just percent time if you wanted to time like an individual line of code, and then 2% and time it will give you a benchmark for the entire cell block. So we can time, for example, our average to df(a), df(b). So we can time our code. And the reason why I'm showing you guys this is if you are doing like numerical calculations, average, v underscore average to mod. So this is really just running the same code that we did before. You can see like just running NumPy vectorize, if you're doing numerical calculation, it's pretty much giving you, at least on this computer, like a 2x increase for free. And if you're using Numba, it is 20 times faster than, so it's 20 times 2, so it's 40 times faster than you rewriting it yourself, right? So there are a few things that, especially if you're doing numerical calculations, it's just worth it. It's like you type in like 10 characters and you just get some speed up for free, right? So that's sort of the really cool thing about using this decorator notation. And since this is PyCon, you'll probably see in other tutorials or in probably some of the talks when they show code, if you see this @ symbol, that's really just, hey, we're taking this function from this library, and this is the function that becomes that function's input, and that's all that's doing. So it's just making a modification there. All right, so I had an exercise, but we're not going to do that because I wanted to at least talk about models. But you can think about the tidy data stuff before, and you know, instead of using str.split, you could have very easily written a function that took in an arbitrary string, split the string using the base Python split function, bracket out the first element or something to get like the case or death count, right? So you can apply a function to the Ebola data set to clean it as well, right? And that's sort of the segue into like, hey, like, yeah, splits, in this case, it's a pretty simple example. You're just splitting by an underscore. But like, let's say you're dealing with, I don't know, some kind of public data set and you're trying to validate, like, is this a telephone number? And writing a regular expression for a United States telephone number ends up being really interesting. Or, you know, if you ever have to write regular expression that's like, is this a valid street address? Like, just Stack Overflow that and just copy and paste it and never look at it again. Because it is like, it's comically funny how like complicated the regular expression is to string match like a valid US address, a street address or something. So, all right. All right, so last 20 minutes, I will show you So I showed you a little bit into Numba, like leaving the Pandas ecosystem. So the last thing, like you've processed all your data, like everyone just wants to fit a model. I didn't show you plotting, but I'm sorry about that. But usually we want to fit a model. So let's show you how to fit models. Import Seaborn as SS. We're gonna use the tips data set again. So I think if you did it once, it should be okay. It doesn't. That's actually never happened to me before. So like I think it's smart enough to know that like if it's already downloaded, like don't do it again. All right. So we'll go over scikit-learn, and then if there's time, I'll kind of show you stats models. All right, so this is another way you can import things into Python. So for this entire time, I've been saying like import pandas as PD, which is like import all of pandas as this alias called PD. Usually when you work in scikit-learn, you don't import all of scikit-learn. You are usually using scikit-learn for a very specific set of functions. And so this is how you can import like just a linear model function from scikit-learn. And the benefit of this is you don't have to say sklearn.linear model. You can now just use linear model on its own, which is why I said in the very beginning, don't use the star, because it'll just import everything, and you won't know where functions are coming from. All right, so think of a linear model. So this is why tidy data ends up being really important, because let's say we're looking at our tips data set, and let's fit a linear model. We're using a linear model because our response, or what do they call it in psych world, the dependent variable, is going to be the tip. So like, let's say for a given total bill, like what do we expect our tip to be? And because the response variable is a numeric variable, it's not categorical, it's not binary, we're using a linear model. So we first have to create this, like, we loaded the linear model function, but we actually have to create like an empty linear model. It's really like instantiating the linear model class. So in linear model, we are going to be performing a linear regression. So now that we have this linear regression object, we now have to say, hey, what are your x's, which is what are your variables, and what is your y, which is what is the thing that you're trying to predict or fit a model to. The syntax is a little weird because the x is a capital X, and that's really just because the mathematical notation of a matrix is usually in capital letters, so it's a capital letter X. I forgot, someone on Twitter like apologized for doing it this way, but it's now so ingrained. But it has like a mathematical reasoning for. So what is going to be our x? So right here, we're going to say we're going to calculate from using the total bill. We are going to calculate or try to predict what is the tip, right? And the y is lowercase because in math world, when it's just a single vector, it's in lowercase letters. So that's why that's like that. Oh, it's not lr dot. It's lr dot fit, sorry. And tips. Cool. Is that the value error I expect? Yeah. All right. So we're going to fit a model, which is why it's lr.fit. When you are, this only happens when you have one column as your x's. You're going to get this thing like this shape doesn't make any sense. And that really is just because of the way the matrix or the way the linear algebra calculations are done under the hood. When you give it one column, it's like one column when it needs it like the other way. So you have to reshape your column, which is what this error is. So if you ever just try to like, hey, let me just see if like this thing works with one column, it just ends up being a little trickier, and this is what that error is trying to tell you. So you have to take dot values because you need the NumPy representation, and it's literally saying like you have to reshape it for this to work. So that's essentially what that error is trying to tell you. All right, so we fit our model. Notice that we don't have to assign it back to LR. It's all being done all within this one LR model objects. So this is, again, this is what happens if you set that in place parameter to true in Pandas. It's directly modifying the data frame under the hood. You don't have to reassign it back. And there's just performance reasons of it not making copies under the hood for that. All right, so once we have our model fit, how do we get the various parameters? So like this is also me trying to teach like statistics in like 10 minutes. So the, oops, it's LR. So the coefficient is the actual thing. If you've taken statistics before, this is your beta estimate. This is the thing that you will interpret. So again, remember that our input or the x's or our predictors is total bill. So the way you would interpret this number is saying for every $1 increase in total bill, we expect the tip to increase by, in this case, like 10 cents or 11 cents. So people in this data set, if we don't adjust for anything, are just leaving like 10, 11% tips, right? There was a hand somewhere back there. All right. This is the tips data set from Seaborn. And then the other thing people will end up looking at is the intercept. You usually don't interpret the intercept. So this is really saying when the bill is 0, the tip is just 92 cents. Like you usually don't interpret this thing. So people are just like by default just giving $1 essentially. All right. So that's great. So if you wanted to fit more models, what you would do is essentially right here. So let's say it's total bill. If you wanted more columns, what's another numeric one? Size. We can put in size. Right. So this is sort of the reason why I don't like scikit-learn too much, because it just gives you like unnamed things back. But the total bill, so this is saying for every $1 increase in total bill, the tip increases by 9 cents, assuming the size is the same. But if the size of the party increases by 1 extra person, the tip increases by about 20% for every 1 person. So that's how you interpret these values. So the last thing in the syllabus was like talking about like dummy variables. And so I picked size specifically because size is a numeric variable. And when you're working with your data and you know that this data is going to be analyzed later on, what you have to do is how deal with the categorical variables, right? So the way I was interpreting that was like for every $1 increase in, for example, total bill, what was the tip? It was about like, the unadjusted one was about like 11 cents, right? So what does it mean for like your smoking status? Like you can't say like for one increase in smoking status, what the tip changes. Like that sentence doesn't make any sense because it's a categorical variable, right? So when you're fitting models, you have to do something special with categorical variables. And the statistics way of saying it is called dummy encoding. The computer science / electrical engineering way of saying it is called one-hot encoding, which is something I didn't know was a thing. So it's dummy encoding or one-hot encoding. This was like, computer scientists are really good at naming things. All right, so how do we deal with dummy variables? And we can see this if we, for example, like put in a categorical variable in there. So we have tips, and if we try to put in total bill, and sex, and then the y is the tips, right? It's the error is literally going to be like, I don't know how to convert female into a number, right? Because like at the end of the day, all of this stuff has to be like converted into a number to do the actual like linear algebra on. So we need a way to convert like this sex column into a number, which is why like if you ever used to work with a statistician before you guys all become data scientists, like they were just like, no, I just need a data set that's really just a bunch of numbers and like a separate thing of like the, that's why code books were a thing, because like everything had to come in as a matrix, right? The nice thing about like pandas and R and all these languages now is like you don't need the code book so much anymore because you can just have strings in your data set. But you still need to have some way of converting everything back into a number to do the actual model fitting. So I'm going to subset the data set just to make it a little smaller. And we'll just look at the these three columns, right? So in Pandas, so if you want to do the dummy encoding in scikit-learn, look up one hot encoding. If you want to stay in Pandas world, which is usually what I do, it's called dummy encoding. And I say that because in Pandas, there is a function literally called get. Did I import Pandas? I don't think I did. Oh, wait, I did. It's just like lagging on me. So if you pass in your data frame into get dummies, anything that's not a numeric or a number, any column that's not a number, it will treat it as a column, and then it'll essentially spread it out for you, right? And the reason behind this, it'll make statistical sense when I explain it. It will take each one of those values in that column and in that one column and make them into separate columns. And the way this data set now is, and the way you'll end up interpreting it is, male will have like, was this person male? 0 is no, and then this person was female. And in this case, this person was male, so female is 0. And the way you'll end up interpreting this in your model is like, instead of like a 1 unit increase of sex, it'll just be like, the baseline status is male, so if the person is female, oh wait, no, if we're looking at this column, if the baseline status is female, so if the person is male, then what is the tip, right? And so what you'll see if you're doing like linear regression, many models will differ, but in linear regression, these two columns really encode the same bit of information. If you're in this data set, if you're not male, you're female, and if you're female, you're not male, right? So in here, in the get dummies, there is a parameter called drop first, and if you set it to true, then you end up with n-1 categories back, right? And that's really important for linear regression because you can't have two columns that are like completely correlated with one another to do linear regression. It's literally violating one of the assumptions. And so now we have this data set that says if this person is female, they get a 1. Then we automatically know that the person is, the other group is male, right? All right, so you'll see that this function, get dummies, it'll work for all of your non-numeric columns. So if we assign it back, now we get that proper dummy encoded data frame back, and then we can fit our linear regression model. So I will just copy this. Oops. Copy this. Oh, it's not sex anymore. Wait, hold on. Yeah. So this is like where that slicing notation ends up being really handy, because usually you end up wanting, usually you put your response variable as the first column, just so you can do, sorry, iloc all of the rows 0, all of the rows 1 to the end. Tips dummies. Yeah, I'm like all over the place. All right. Yeah, so now we don't get that error anymore because male female is now encoded as a proper like numeric value. So now if we look at the coefficients, so the first one was total bill and the next one was sex. So now we can say like for every 1 unit increase in the total bill, the tip will increase by 10, 11 cents, assuming that the gender didn't change. Or we can look at the second variable, which is sex female. So this is saying when it goes from 0 to 1, which is saying that if your party is, I'm assuming, I don't know how it works for multiple people, but if there's one person and this person is female, compared to males, they will tip 2 cents more. Or 3 cents more if you're rounding, right? So that's how you interpret those values. And that is the... Oh, is it? Is that how that data set works? I have no idea. I've actually never looked up this data set. So I thought, huh, that makes sense if the gender is the server gender, because I've always wondered, like, how do they genderize, like, parties of 3? Okay. Yeah, the smoking thing makes sense. Yeah. Okay. Yeah, I've used this data set so much that it's like kind of weird that like I've never thought about like what I'm doing because it's always like done as an example. So I never like properly looked into what it's actually used for. All right, so that's pretty much like the intro to pandas. The most important thing was like that tidy data section is probably the most important thing to understand like what you need to do to process data. The function stuff is how you just generalize it to processing data for whatever use case. There's some things I didn't really cover. So for example, I didn't explicitly show you all the ways like joining and merging works. I would say take a look at how concatenating works. It's very different when you're concatenating, like literally stacking rows or columns. Pandas does something pretty interesting. So the reason for why you would want to concatenate things is, let's say you have a really long data set and it just gets broken up into many pieces. You need to put it back together somehow. For example, like stock data, you'll get one data set for each day for a particular stock and you want to analyze it across a month, you need to tack it all together. That's where, so pandas will do automatic alignment. So when you're concatenating things lengthwise, so you're making your data set longer, your input data frames, the columns do not need to completely line up. It'll automatically align them. If you have columns that don't exist, it'll just create that new column and everything else will be filled in as missing. So it does a lot of that stuff for you for free. The tricky thing is if you want to concatenate things like on the side, it also does automatic alignment on the index. So that's something you really want to be mindful of, like, does the 0 actually correspond to that 0? Because if it's somewhere else, it's gonna be moved around, right? So that's something you really want to pay attention to when you're concatenating. And then there's stuff about plotting. I personally use Seaborn, but then if I end up having to plot something like super serious, like I just leave Python altogether and I use ggplot in R. That's just how I was taught, and I just kept doing it that way. So I am not the best person to teach you plotting because I would just say like learn R. In the tutorial, so I'll post up the actual stuff I typed up today during lunch when I can install other stuff on this computer. The only thing that's actually missing that I didn't really cover, so I showed you everything that I wanted to show you, which was scikit-learn. But if you're used to other programming languages, statistical languages, stats models is It allows you to specify the predictor, your predictor, so like total bill and sex, and then your response in this like tilde notation, which is very, if you worked in R, this is what it looks like. That's cool because it will automatically do the dummy variable stuff for you. And instead of looking at .coef and .intercept, it actually gives you the proper like statistical like output. So if you're used to looking at statistical output, I would say go to this notebook and just scroll down past scikit-learn. The reason why it's like this is scikit-learn, the paradigm is like this was made by computer scientists. It's really good at doing predictions, so you don't really need all of this stuff if you're just doing predictions. And then stats model is really written by statisticians, which really care about inference and like, is your model like quote unquote correct? And that's why it's just two schools of thought. You'll have a few more of like your traditional, both sides can do your traditional statistics. Scikit-learn will have more of your machine learning stuff. If you want to go down the machine learning route, the scikit-learn like documentation is actually really, really good for that if you just want to learn about that field. And the last thing in here is there's actually like, if you are really used to this tilde string notation for creating and setting up your predictor and your output and your response matrices, there is this library called Patsy, which is what's, I think this is what stats model uses to, for a given string that specifies how you want to split your model, it'll give you the two matrices of like, what is your thing that you want to model, and then the all your predictors with the dummy variables encoded. So that's what this little thing about Patsy is doing. And you can use Patsy, if you're so used to this notation, you can use Patsy to just feed in your scikit-learn model that way as well. So that's more statistics things. That's kind of out of scope, but we're also out of time. So that is our tutorial, and hopefully it segues you into all of the other tutorials that you guys are taking for the rest of the next couple days.